Hey, welcome to the exciting part. In this presentation, we're going to look at how statistics can help us answer some questions like, what about up here? Do the trained players have better breathing power than the untrained players? Playing musical instruments and improving the time that you can breathe through the instrument. What about that? And over here, the sort of questions, how should you be using your tennis or basketball court that you're hiring out to the public? What's the use on the weekends, the daytime and the evening between tennis and basketball? What do people prefer to use? So you can see there are a lot of things that we can compare here, and there's lots of ways of doing it. And just going around the screen now, let's come over here. What are the two variables involved here? Well, there's girls or boys. That's categorical. And then there's some discrete data here, the scores they're getting. And that's discrete data down the bottom. And we call the value down the bottom here the independent variable. And then up here we've got the number of times it occurs. Over here, the trained and untrained players, they're categories, but then there is discrete data in here, isn't there? The discrete data is measuring the variable of how long that they can breathe through their instrument. And over here, these are categories. Okay, so these are the independent variable, and this is the percentage use that people have for those basketball or tennis courts. And that's a continuous variable. Here's another one down here, a representation of the players training to blow through their instrument here. Trained players or untrained players. That's a categorical variable, but then the time that they can breathe through their instrument, well, it actually could be continuous, couldn't it? I said up there it was discrete. Depends on how accurately you can measure that time. It could actually be continuous data. So we've got, usually in these problems, we've got two variables that we're measuring, whether it's boys or girls, and then something else about them, the score. Okay, that sort of thing. So let's go down and try and develop that a bit, because we can use that to answer all sorts of questions about who's going to win the next election, who's done better on the golf course, and so on. In the long run, you know, if you compare your scores to somebody else, and you might have a lot of low scores, but overall their group of scores is lower than yours, so they've done better. How do you tell? Interesting questions. So come on down now, and let's have a look at an example here from Hayes and Harris Publications. So here we are, 50 volunteers participate in a double-blind trial to test a drug to lower cholesterol. A double-blind trial means they're going to switch the people around, double it up if you like, and blind means they don't know whether they're getting the drug or not. And it's often called a double-blind crossover. So in a double-blind trial, neither the volunteers nor the experimenters know who was given what treatment. That's a double-blind. So neither of them know when they're treating them what they're giving them. So we've got 25 volunteers were given the medicine, and the other 25 were given a placebo, which was a sugar pill that looked the same as the drug, but would have no effect at all. The results are summarised below. So, in other words, you can't let the people or the experimenters have any psychological advantage and maybe help the drug work or something. They don't know whether they're getting it or not, so they're all equal. Get the idea. So here's the first set of data. Cholesterol levels of the people who took the drug. Second set of data, cholesterol levels of people who took the placebo, something, it's a substitute for the drug. Okay, what are the variables? Draw back-to-back stem plots so we can compare the effect of the drug and nothing on the people. Does the drug have actually any effect? Draw parallel box plots. Interpret the result and make a conjecture. So a conjecture is your proposal or summary of what you think is going on there. Consider the underlying assumptions. Okay, let's go down and have a look at what happens. So here the independent variable is the categorical variable treatment. with or without the drug. Did they get the placebo or drug? 2 categories. The dependent variable is the continuous variable cholesterol level, because we see that that's going to be dependent upon the other one. Okay, so 2 types of variable there. So the data is close together, okay, and we want to use a stem plot, so we're going to split it. In other words, that's 3 and 3 star, 4 and 4 star. Okay, so the 3 is equivalent to less than 5. Okay, so 3 up to 3.49999, and 3 star is equivalent to 3.5 up to 3.999, that sort of thing. So we spread them out a bit more. Okay, so listing them out, there's the ones with the drug, and here's the ones with a placebo. And don't forget your leaf unit, some statement here about what the meaning of all that is. So you have the stem, remember, and the individual scores are the leaf entries. And you can see it looks like down here the placebo has left the cholesterol fairly high, whereas the drug results are lower. That's our initial observation there. Okay, so let's go down and have a look at the box plot. Does that agree? Oh yes, that's making it a bit clearer. You won't have to worry about these outliers. There are 2 outliers, but there's little overlap, is there? So here there's a little overlap between the groups. So they don't affect the conclusion, so we don't probably have to worry about those at all. Could be errors in measurement, or some individuals having a different effect there. Those taking the drug. Now look at these steps. Lower median cholesterol levels. So there's 0.1. You compare the medians of the 2 groups, and it's significantly less. It's also got a smaller interquartile range here, the length of the box. So we're going to talk about this in a very structured form. So this is part 2. And so we're going to make a conjecture because of the 2 medians difference. Then we are making the conjecture, the proposition, that the drug did have a significant lowering effect on cholesterol, and from the IQR we could conjecture that the drug made the cholesterol more uniform. Okay, so they were generally less and more spread out, more consistent, more uniform. Okay, so that's our 3rd point. But I'd like you also to possibly get into the pattern of talk about the whole gap between the boxes. So we can say, well, in this case, apart from the outliers, all the people taking the placebo had higher cholesterol levels, so this doesn't even match here, than the people taking the drug. So I would like you perhaps to make that 2A and talk about the position of the boxes, okay, or of the whole distribution. Do you get it? We'll come across that again. Okay, any assumptions? We'll assume that the group of volunteers had similar cholesterol levels before the trial. Okay, and that the lowering of cholesterol was due to the drug and not to bias in the sample. In other words, they didn't by chance have people who had lower cholesterol. Randomness of the selection procedure should have made such bias very unlikely if they'd just taken it random. Okay. But the cholesterol level of all volunteers should also have been recorded before the experiment, because these dudes might have naturally been higher up here. Okay, get the idea? So we've got to be analytical here. This is the exciting part of statistics here, where we can actually give some idea of what's going on, comparing data, comparing groups, comparing opinions of who's going to vote for somebody in an election and so on. Okay, so let's have a look at some questions here. 5i from Hayes and Harris Publications textbook. And we're going to try to answer this question. We'll start with a question. And we're going to say plain chocolate frogs are sold in bulk and sell for $2 for a pack of 5. And chocolate frogs are in, fancy ones are sold at 50 cents each. Okay, we want to look at the weights of the frogs. Do you get a better deal buying the ones in fancy paper? Okay, so the question is, which would be more economical to buy? So you're going to do an analysis. All right, pause the presentation, have a go, and down below after all the questions there, I've got some answers for you. Okay, let's have a look at the next question. Question 2. Taxi drivers are arguing about who makes more money. And they're going to compare 25 days of work. How do you work this out? The average, the median, how would you compare? On some days one might make a lot and not much on the other day. Let's have a look at it statistically. Okay, have a go. Go on now. Question 3. Okay, so survival times for rats being tested with anti-cancer drug. Important sort of work, isn't it? You have to justify to people who are giving you money for research whether your research is effective. Okay, pause it, have a go. Coming down now to question 4. Fertiliser plots. Did it really work? Is it worth it? It might seem to be higher, but what did it cost you to apply this fertiliser? Read the question carefully. Okay, I'll just scroll down now and give us just a little bit more. There we are. So there's your data set, and you're comparing them. Okay, sorry about that. All right. Let's go on and have a look at the answers. Okay, question 1. I'll just go down a bit. Question 2. Have a look at question 3. Just check your plots. And just going down to question 4. And let's do another example. Okay, here's another one. See if we can come up with a statistical analysis of this one and a conjecture, a proposal as to what has happened. Okay, an educational researcher believes girls are not as good at science as boys. Okay, to study this claim, 40 13-year-old girls, 40 13-year-old boys were selected to answer 20 basic science questions. So we take it these students were taken at random. So we weren't picking out particular classes or anything. No bias. The results of the test are shown below. So here we have the boys' scores, the girls' scores. What are the variables? Plot a column graph. Make 5 number summaries. Parallel block plots. This is a good analysis here. Calculate the median, interquartile range, the mean and standard deviations. What conclusion can you draw from the analysis? So lots of work on the calculator here. Okay, so come down, let's have a look at doing that now. Okay, the independent variable is the categorical variable gender, male or female. 2 values, either girl or boy. The dependent variable is the discrete variable, number of correct answers. So it's numerical, but they're only separate things. You can't get 1.5 answers. So it's discrete. Technology now. We'll have a look at how to do this with technology. Just notice there a column graph for the boys and the girls. The columns are all separate because that indicates, unlike with a histogram, discrete data. Okay, and up here the number of people in each group. Don't forget to label the axes. Score. Okay. We don't usually label this axis if it's just a number, unless it's a percentage. And if you change it to a percentage, you'd write percentage up there. Okay, 5-number summary from the calculator. Putting all the data in, if you're Casio, list 1, then go to calc, and you've got to set it up on list 1, and then you get these values, the 5-number summary way down the bottom. Okay, part D, the boys and girls stem and leaf plot, box plot, sorry. Okay, so the box plot here has 2 outliers for the boys. Remember what an outlier is. You can get the calculator to tell you, or the upper limit of how high the score can go before being considered outside or lying out from the main body of data is the upper quartile Q3 plus 1.5 lots of the interquartile range, and the lower quartile is, or lower limit Q1 minus that 1.5 times interquartile range, which is the width of the box plot, of course. Okay, so we've got some good comparisons there. The information summarised down here: median, interquartile range, mean and standard deviation. Okay, what's our conjecture? Well, they're looking particularly at the summary statistics found in E. Doesn't show any clear difference. Now, is that in agreement with what we've got here? Well, the medians are very similar. The lower quartile is similar. Looking at this, see how similar that is. Now, there's only one major difference here, Q3, also a little bit higher here. So we would say, if you go through those points of discussion, median, and then the spread with the interquartile range or the standard deviation, and then talking about the position of the box plots. They haven't done that very well here. Doesn't show any clear differences. From this we can say there is no difference between boys and girls answering questions in science. So you could mention that the spread, there's the interquartile range, and also the standard deviation. We could mention the girls are slightly more inconsistent, possibly. Okay, there, because it's quite clear that is a bigger interquartile range in the box there in the middle. But nothing much else. Probably not worth talking about this height here, because we've got one outlier, but we've got a few more girls in this upper region. Very, very similar. Very hard one, this one, to make a conjecture. So we'd have to make an error, that is, on the side of saying there's not much difference. All right, are you ready? Here's yours. Question 5 athletes times. Okay, so have a look. Are they categorical, numerical, discrete, and continuous? In numerical, remember, if you can have any score in between, it's continuous. If they have to be discrete scores, it's discrete. Yeah, obviously. Okay, so have a go, and I'll go on and show you the solutions. Here we are. How did you go? Making a conjecture. Okay. Let's go on and have a look at some just general comments now. Now, they've chosen in this section data sets which are very similar, very different. Here, for example, in those 2 samples, if you went and did the 5-number summary and also got the standard deviation, remember that's sigma for the population, and there's sigma and SS. Usually on the Casio you use SN because it's just a sample of the whole population, and you use sigma when you have the whole population. So just doing all those statistics, you can't see much difference. See here the median, 0.5 in 10. That's not a very big shift. Interquartile range, or slightly bigger here. Mean, very similar. Standard deviation is slightly different. So you might say sample 2 is a bit less consistent, a bit more variation in sample 2. but also sample 2 is a little larger than the that of sample 1. But the difference could be due to the random nature. So here, very hard to say, isn't it? There's a little bit of difference here, a bit of difference in the standard deviations. Very hard to say. So you'd usually say we need more data. So to decide whether the difference is unlikely due to chance alone, you've got to use hypothesis testing. Okay. Well, you'd need a bit more data, and also you could use hypothesis testing, but probably you go back and say, let's collect more data and just look at how we're collecting it as well, making sure it's precise and there isn't a bias in it. All right, so keep that in mind. In other words, what we're saying here is this is not the only way of comparing data sets in statistics. This is a very basic way, and we go on to much more elaborate methods later on. So hope you are still around for that. Okay, let's have a look at particularly comparing categorical data. Okay, so here's something that you might do if you're running a business. A court in a recreation centre can be used either for tennis or for basketball. The manager wants to make best use of this court. When should the court be used for tennis, set up that way, and when should it be used for basketball? So, the manager decides to look at these 3 groups. Coming during weekends, coming Monday to Friday during daytime, coming Monday to Friday in the evening. He's going to survey them, which of course is a fundamental idea in statistics. Okay, so the manager decided to ask the questions using the centre, asking the customers when they want to use the centre. So collecting the data, he put a sheet of paper by the front office for customers to fill in their preferences. We'll have to talk about whether that's a good way of actually collecting data. Anyway, so he said, write down the time you normally use the centre, which sport you prefer to play. Time, you could choose weekend, daytime, evening. So if I come on the weekend, I can say what I prefer, tennis. Come in the evening, I fill in basketball. Daytime, tennis, etc. So he's going to have to analyse this data in some way. So let's have a look at the groups. So you can put in a table. Okay, so here's weekends, tennis, basketball. Daytime, tennis, basketball. Evening, and so summarised it nicely there, and the total number of people using it weekends, daytime and evening has been summarised there. This is called a two-way table, okay, because you've got to read it in 2 directions. There's a variable listed here and another variable there. Both categorical variables, aren't they? Okay, so each entry is the number of people representing those 2 categories. So you can see here the categorical data, all of it is categorical data here. 2 related variables, here we are, time and what you play. Okay, so there are 6 possible combinations. Each of these 3 could go with each of these 2. Now, to compare them, they've suggested here putting percentages in. So 19, and I'm going to go back up here, let's look up here. 97 people are usually on the weekend, so 19 out of 97 times 100 is the percentage using tennis, wanting tennis. And so it could go through to everyone. 23 out of 32 times 100 over 1 would be the people wanting to use it in the daytime for tennis. So these 2 numbers here must add up to 100% for the weekend people. These 2 here must add up to 100%. These 2 here. So you're changing them all to percentages, and then you could draw this column graph down here. Weekends, daytime, have a gap between them. The evening, gaps in here because they are separate categories, and percentage use. So 20 plus 80 should come to 100. So each of these totaled should be 100. All right. So let's have a look at how you do that with technology, and over here Excel. So come down and look at Excel here now, and see how we go. So if you open up a spreadsheet, a new sheet, okay, and enter the data. So this is what a spreadsheet looks like. Columns and rows here. So you'd list down here weekends, daytime, evening, tennis, basketball, and put in the numbers. They are not using percentages here. Not using percentages, using the raw numbers. You could change that if you wanted to. You could put in here equals B2 divided by D2 times 100. You can get a spreadsheet to change those to percentages if you want it like we just did it by hand with percentages there. Then there's a little icon up the top, and you can click on that to draw a chart. And the one that you would choose is the column graph there. So it would be highlighted like that. There are other interesting ones you can do, but generally people like a fairly simple one so they can understand it. Okay, and then you actually can label the axes and so on if you go in there and play there, and when you finish you get this. Notice these are not percentages here. I haven't done it the same way in this example. So weekends, how many of each group, daytime, how many of each group, and so on. But not as a percentage. It might have been better to compare using percentages, although you can see quite clearly the change in use required weekends, daytime and evening. All right, what have we just achieved with that survey? Are there any limitations? So here we are, interpreting the results and forming a conjecture. Here we are, about 75 to 80% of weekend users prefer basketball, whereas only 30% of the daytime players prefer this sport. Manager decides to use the court in proportion to the interest. So he timetables the court for tennis on Sunday morning for the 4 daytimes, Monday, Tuesday, Thursday and Friday, and for Wednesday evening. The other times the court will be used for basketball. Okay, so he reckons, he conjectures, his proposal, his proposition is that this is an accurate reflection of the interest of its customers, of the centre's customers. Now what's being assumed here? One assumption is that the number of people who show an interest in the use of the court reflects the amount of time the court should be used. Now there's a problem with that, isn't there? You might want to play basketball, but it's a team sport. It involves more people than a game of tennis. What if you don't have enough basketball lovers there at the right time? It could be more difficult to schedule this. So you have to examine that. What about the way he conducted the survey? Was that adequate? Putting a sheet of paper on the front bench there? I don't know. Maybe people didn't see it, didn't have time to fill it in. Okay, what would have been better? Have you any ideas? Talk about that. What would have been better? Making sure that when people came in and swiped their card to get into the centre or paid their money, you could ask them. Okay, so that everybody using the centre was surveyed. Okay, interesting, isn't it? So thinking about data collection is very important if you're going to obtain a sample and therefore get a good estimate of the population without any bias. Okay, I hope some of these words are clear to you now. Okay, let's look at another question here. A couple. Question 6. Giving us categorical data, and this is a 3, down here, a 4 by 3 table of categories there. Okay, and the number of people falling in them. So I think you should try to go for percentages. Okay, that's what it asks you to do down here. Okay, pause the presentation and have a go. Come down and let's have a look at the next one. Question 7, same idea. Interesting, surveys about who's listening to our radio station so we can play more appropriate music perhaps for that group. Or maybe change it and try to attract more of a different age group. Important questions, aren't they? in running a business. Let's have a look at our answers there and the sort of conjectures we can make for questions 6 and 7. Okay, well, let's just finish off with a little bit down here. Now come down here, and often you want to do your own project and conduct your own survey or get data and so on, and come to some conjecture, make some proposition, and you might want to write a report on something. Okay, now you should, in writing a report, remember a few points. First of all, you should have a question that you're trying to answer. That's very important. What are you actually trying to do? Because that's going to affect the way you collect the data and how you analyse it to a certain extent. Now, other than that, writing a report, keep your language simple. Short sentences are easier to read than long sentences. Stick to the information and don't go overboard and say you're doing things that you can't really conclude from the way you've collected the data or what the data really says. Do not use personal things. I collect the data. Rather, you say, this is the way to do it. The data was collected, is what you say. Okay. Okay, so it's extremely important that you don't make it a personal statement. It's impersonal. It's got to be scientific. Well, really, that's a tradition in science, but mathematics is a very important, in mathematical analysis, important that you stick to the data and what you can reasonably conclude, not bring in your personal opinion. Okay, so you don't draw any criticism of yourself. Okay, it's purely based on mathematical principles. Okay, so let's have a look and just finish off with this one example, and then you might like to do your own project on this. What do? We state the problem. Okay, it was examining the effectiveness of the cholesterol lowering drug, formulate the method, describe how the data was collected, collect the data. You may add the actual raw data as an appendix, but you're probably just going to use statistics, that is, values quoted to describe the pattern of data, rather than the actual data itself, and graphs, of course. And then you describe how the data was collected there, and then, of course, the analysis. So it's all in sections, and you can put these title analysis and clearly labelled graphs. And then, of course, interpreting the results. Okay, don't forget, this is what a lot of people leave out, the stem and leaf unit. Okay, interpreting results of 3 or 4 points in there about the comparison of the graphs, the 5-number summary, that sort of thing. Underlying assumptions, we had a look at those. Volunteers had similar cholesterol levels, and that the lowering was due to the drug and not to bias in the sample. Randomness of the selection, you are equally likely to get high or low cholesterol people coming from your sampling procedure, making bias unlikely. Okay, but cholesterol should have been measured at the beginning of the experiment. Okay, and then a conclusion. That's your final conclusion. And here it can be seen that the drug lowered the cholesterol level. That's your conclusion or conjecture. Here there is, however, that one subject dropped as low as 3.2, and that could be dangerously low. It's recommended that if this drug is to be used, patients are monitored for possible harmful side effects. So that's not bad. All right, so get the idea. We're getting to a point where you can do some useful statistics that will be meaningful to other people. So I hope you're getting happy with your skill level now, because you're actually coming into an area where you are useful as a young statistician. So keep going then. I'll just get rid of that, and I'll catch you a bit later on when we look at some of those other probability distributions and going a bit further with statistical analysis. Cheers for now.